Hello, my name is Christian Helm. I'm from the University of Tokyo, and I will introduce our work on the automatic identification and precise attribution of DRAM bandwidth contention. Now, this talk is about performance optimization. And we know that many applications don't reach the peak performance that the hardware actually promises. And we also know that many of the applications are bound by the memory bandwidth. And these types of problems originate from the interaction of software and hardware and are thus very difficult to find. And one of the specific problems I want to highlight is DRAM contention. Now, DRAM contention means that we have more demand for bandwidth than there are resources available, which means that we have multiple cores that compete over the single bandwidth resource. And I want to highlight the fact that consumed bandwidth cannot identify contention. And as an example, if we assume an application uses 95% of the available bandwidth, the bad situation, the contention case, is when the application actually requests more bandwidth than there is available, and then there is the good situation where the application actually gets everything it needs and all of the resources are just perfectly used. And just by looking at the consumed bandwidth, we cannot differentiate those two situations. We also often use NUMA systems, and NUMA systems have their own individual DRAM in every node. So in theory, we could achieve a higher aggregated bandwidth. However, this requires that we also use all of the available DRAMs. For these problems, I want to highlight our contributions. First of all, a method to identify DRAM contention and imbalanced NUMA resource usage. And this method can differentiate the harmless high bandwidth consumption from the actual contention case. It also has a precise attribution of the contention to individual source code lines and objects, and it contains a contention severity metric and also a NUMA imbalance severity metric. Our approach is also practical because it's implemented in a lightweight profiler with low overhead, because it runs on single socket and NUMA systems. It also runs on any default Linux OS and works with ARM modified code and only needs debug information in the binary. Next, let me introduce the related work. First of all, for contention detection, there is the very naive approach of measuring the consumed bandwidth. However, as I explained in the introduction, this does not identify contention. And because it's based on performance counters, we cannot get the precise attribution. There is the concept to use latency as an indicator for memory problems. However, this does also not identify contention. It just indicates some type of memory problem. However, we can get the precise attribution because those approaches are based on instruction sampling. Next, there is the performance counter-based detection. So those can really identify the contention. However, because they're based on performance counters, we don't get the precise attribution. And finally, there's one instruction sampling based contention detection approach that's using machine learning based on latency and some other features. However, this was only demonstrated for remote memory contention in NUMA systems and not shown for any local memory contention or single socket systems. Also, with this previous approach, the severity of the contention cannot be quantified. Now, for NUMA imbalance, there is a previous approach that can show the location, allocation, first touch and use of data. However, this doesn't contain a quantification of the imbalance. Then there is the visual detection of imbalance, where there are different types of visualizations proposed to identify imbalance in the resource usage. And finally, there's an OS extension, so it's not a profiling tool, but it contains an imbalance metric, and they use the standard deviation of the load across nodes. Next, let me introduce the actual contention detection method. This contention detection method is based on the relationship of bandwidth and latency. And it is known in queuing theory that if we have arrivals to a store and there are only very few arrivals, then the time that one customer needs is only the in-store processing time. But if we have many arrivals and the queue in front of the store fills up, then we will have the queuing delay in addition to the in-store processing time. And we can apply the same thing to DRAM. So we have an application that issues requests that go into a buffer and then to the DRAM. If there are very few requests, we only have the in-DRAM processing time. But if there are many requests, the buffer will fill up and we get the queuing delay in addition to the processing time. How to measure the latency that an application experiences. The hardware instruction sampling actually contains the latency. However, we can not just use all of the samples that we capture, but we need to select the right samples. This table here shows an example of sampling data where each row is one sample and each of the column is one of the attributes we're going to use. Now this first sample, we see that there's a hit in the L2 cache, and we want to exclude all the cache hits because we're only interested in the latency that comes from DRAM accesses. So we exclude this one. The second one here has a TLB miss, and a TLB miss causes additional latency that we don't want to include in our latency measurement because we're only interested in latency increase that comes from contention. Similar, this third sample, which has the locked attribute set, which means that there is an hardware atomic access, which also has a very high latency unrelated to contention, so we also want to exclude that. Now here in this example we have those two samples left, and in reality we take the average of at least 25 samples to calculate the latency. And because we have the instruction pointer here and the data address, we can have a precise attribution within the program context. We did an additional evaluation of the attributes of this measured latency and how it can be accurately measured on current hardware, but this is described in a paper that we have previously published. Relative latency metric. We already know the latency that the application experiences, but we want to know the latency of the DRAM processing. And this is what we call the system latency. So this is the latency of an uncontended DRAM access. We determine this latency with a pointer chasing benchmark. And then we calculate the relative latency, which is simply the application latency divided by the system latency, which then gives us a hardware independent severeness of the DRAM contention. Here, values higher than 1 indicate a contention problem. Our NUMA imbalance metric, I will show again an example based on sampling data. Here we have again 4 different samples, and first we see that each sample has the CPU ID, so we can find out the origin node of each access. Then each sample also has the information if a local DRAM or a remote DRAM was accessed. For local DRAM the information is clear, but if the information here says it's a remote DRAM, we actually don't know which of the remote DRAMs it is. Because, for example, in a 4-socket systems, it could be 3 different remote DRAMs. With this limited information, we calculate our imbalance metric as follows. First, we calculate the local ratio for every node, which is the number of local accesses divided by the number of total DRAM accesses. And then we calculate the NUMA imbalance metric by using the maximum of the local ratios and subtracting the minimum of the local ratios. And this then gives a range between 0 and 1, where 0 is a low imbalance and 1 is high imbalance. For the implementation of a profiling tool, it's mostly based on Linux Perf, which provides most of the features that we need. However, a few things are missing. And this is first, it cannot resolve the dynamically allocated objects. So we add an allocation tracker that also profiles the application. And after the profiling is completed, we merge the data into a SQLite database to have easier access to the profiling data and then put it into a new analysis method. Next, for the evaluation. So for our evaluation, we used 4 different systems. And for some of the evaluations, it will be interesting to know which one is the fastest and slowest in terms of memory speed. So I will use these stars here to mark the fastest system with a 1 and up to the slowest system with a 4. To evaluate the contention detection method and our severity metric, we need 2 things. First, we need a benchmark that can create an adjustable amount of contention. And then we also need to quantify this contention to compare it with our severity metric and with our detection results. The adjustable contention benchmarks, simple but memory-intensive parallel vector operations, and they are called count_v, .v, and sum_v. Count_v counts the occurrences of specific values in a vector. .v is a dot product, and sum_v sums up 2 vectors. We configure them with 2 different data sizes. First one, a data size that's smaller than the L3 cache. So this is the optimal case when the DRAM bandwidth is no limitation. And then larger than L3 cache. So in this case, we can see the effect of the limited DRAM bandwidth. And also we use a different number of threads because more threads will increase the bandwidth demand of these benchmarks. And when we look at the speedup, we get a diagram like this, where the small array versions of the benchmarks all scale almost linearly. However, the large array versions, they are limited in their parallel scalability because of the DRAM contention. Now we still need to quantify the amount of contention, and we do this by using the speedup loss, which is the speedup of the small array version divided by the speedup of the large array version. So it basically says how much more speedup could we get if the DRAM contention would not be an issue. And this metric then expresses the severity of the contention. Next, I will introduce the detection results. So we have repeated each experiment with different sampling rates and then repeated each of them 10 times and recorded in how many cases the contention was detected. And this diagram here shows intervals of speedup loss. So here this first bar is from 1 to 1.25, then from 1.25 to 1.5, 1.5 to 1.75, and so on. And we see that a low speedup loss is not detected, but as the speedup loss gets higher, it's detected in 100% of all cases. And this diagram is only shows only the result for one specific sampling period, but the paper contains the evaluation also for other sampling periods. Now I want to highlight again the advantage of the latency measurement over the bandwidth measurement. I will show in the following slides information from 3 different sources. First, from the bandwidth measurement, second, the latency measurement, and finally, the true information from the speedup loss. And when we look at the consumed bandwidth, we see that with an increasing number of threads, the bandwidth demand increases and then quickly saturates. And we also see that it's very similar for all of the three benchmarks. So we could conclude that all of the benchmarks suffer from the limited DRAM bandwidth. Now let's look at the latency data. So this horizontal line shows like the reference, the system latency. And the different lines here show the latency of the different benchmarks. And here we see that .v actually has higher latency than SUMV, which has again a higher latency than COUNT-v, which indicates that actually the DRAM contention problem differs between the different benchmarks and is most severe in .v. And when we look at the true information from the speedup loss, we see that there is indeed a difference between the speedup loss of the three different benchmarks. And this information we could only get from the latency measurement, but not from the bandwidth measurement. Next, let me introduce some case studies. The applications that we looked at are first all of the 13 parsec benchmarks, and then also N3LP, which is a neural machine translation application. Contention was only detected in 2 of the parsec benchmarks, in stream cluster and CNEAL, and in N3LP. And in stream cluster we see that the fastest system has a latency below the contention detection limit. Then the medium range systems are around the contention detection limit, and the slowest system has a latency above the contention limitation. For CNEAL we see a similar picture. The 3 fastest systems are all below the contention limit, but on the slowest system we see that relative latency is above the contention detection limit. And in N3LP we see a high latency on all of the systems. Now next we can look at the NUMA imbalance metric. We see that stream cluster and CNEAL have high NUMA imbalance, which indicates an imbalance problem, but N3LP only has a low imbalance, which indicates there's only a small or no imbalance problem. So what we can do to fix a NUMA imbalance is apply interleaved allocation. And here we see the speedup after applying interleaved allocation. In stream cluster, we saw that we had high relative latency on some machines and high NUMA imbalance. So the interleaved allocation results in a large speedup. The speedup is higher on the slower systems, and also those systems had a higher relative latency. Now for CNEAL, we see that relative latency was high only on speaker, but the NUMA imbalance was high on all systems. And consequently, we only see a speedup on the slowest system speaker. For N3LP, we had a high relative latency, but a low NUMA imbalance. So as expected, the interleaved allocation only brought a very low or no speedup. The overhead of the profiling tool is at most 12% with a sampling period of 500, and it is a little higher with a higher number of threads. But for higher sampling periods, it then decreases about 8%. In conclusion, we introduce a new method to identify DRAM contention, and with the 2 metrics we can give optimization guidance to users. So first, if the relative latency is low, we know that there's no contention problem. If the relative latency is high and the NUMA imbalance is low, we know that there's a contention problem, but it's not NUMA related. And if the relative latency is high and the NUMA imbalance is also high, we know that there's contention due to the inefficient NUMA usage. And our future work will be to include more hardware related reasons of DRAM contention.